And it gives me special pleasure to work with Professor Misra because he is one of my own former teachers. And even today, the things I learned from him and distributed computing about 20 years ago, I find are too advanced for the modern world, but still just getting to be of the time that I can benefit from them and hopefully make sense of them in practice. So I'll turn it over to Professor Misra to talk about his new work, the ORC language. And in particular, with the topic, I think the title is Structured Wide Area Programming.
Thank you, Maninder. It's always a pleasure to see when one of our students have done well, and you seem to have done very well. I'm very glad to be here, and as Maninder has diplomatically pointed out, the thing that I'm going to talk about now seems to have no application, will have no application for the next 20 years. Now I believe that I will hope to see some of its applications before I die, and I'm not planning to live 20 more years. So let me start with. Am I going to get a feedback like this all the time? I see. Let me start with a small example.
I was there on this, and he got his chair.
Here is a program written in my language. As you can see, it's a very short program, 2 or 3 lines. And let's run the program. I won't tell you what it does, but let's run it. And what it's going to do is search. And let's search for someone famous.
And I'm not hearing the echo, so I'm not going to know when it goes away.
I think it's coming from you, Chad.
He's not very good.
NC Rand.
How can it come from me? I'm not a site.
NC Rand.
Oh, I see what you're saying. Okay, got you.
Thank you.
Okay, this is a little program that I ran, and what it did was to search both Yahoo and Google at the same time for that phrase that I put in Threadbook. It, whatever site came up with the first set of answers, it output those answers, and it output them in a particular form, taking out the hyperlinks and just making them into text and only the first line and such things. The point I want to make is that if you describe this problem to someone, intuitively they will say it's a very simple problem. You search both sides, and whoever comes up with the answer first, you output that answer. But if you actually go and write this program in Java or some language, it will be a huge undertaking. And I wanted to change that, and this is the kind of program that I would like to write. It's about 4 lines, and it says you prompt someone for a search term, and then you do this for Yahoo and you do it in Google, and where Yahoo and Google are defined are in this file. Yahoo is just a link to some site, and Google is a link to some site. And what I'm going to talk about today is how we can make this program work, what their capabilities are, and what we have achieved in the last few years in actually solving problems. Let me take one more, just one more of these. Let's make it a little bigger. Can you sort of see? There is a website somewhere called Eliza. Eliza was sort of a program written in the 60s, and it faked a psychoanalyst. You could give it a sentence, and will, roughly speaking, scramble that sentence or play it back to you, in the meanwhile sounding intelligent or pseudo-intelligent. And people who didn't know anything about computers got very impressed with it. So for instance, here is the Eliza prompt. How do you do? Please tell me your problem. And so if I run this, move it a little. Okay, please tell me your problem, and let's say, what's your problem? Let's try something like this. Oh. Okay, so it will go on with these kinds of things. I don't want to sort of talk about Eliza here. The point I want to make is that this particular program is now available on the web. Anyone can go and ask it, give it some kind of an input, and it comes back with some kind of an output. And we can leverage that program and write a very small program to get its effect here. The program, as you can see, is about this long. This is all of it, nothing else. The Eliza site is defined somewhere above, I suppose. Yeah, this particular file includes the path to Eliza, and you write a small program and get the effect of Eliza. The reason I'm showing you all this is that at one point I decided that one of the ways people will use the internet would be to just 1 second, let me get this input. That currently we use the internet more as a giant communication device. We use it to send a message, or we use it to download stuff. We don't use it in a large collaborative manner yet. We don't take its functionality and put them together. So I wanted to solve the following problem. Someone said that the internet is a computer, and I wanted to actually make that happen. So consider, for example, that we have different kinds of services available at different sites on the web. Let's say there is a service that someone has written on inverting a matrix. And here someone has written another service that can take a compressed file, music file, and uncompress it. There is a service that someone has written which can check the spelling of a word and provide a correction. I expected that in about 5 years' time, we'll have 100,000 of these services of different kinds available. So consider for a moment that each of these services is the primitive operation of a computer. Like today's computer, add, subtract, multiply kind of thing. These are the primitive operations. And on top of these primitive operations, we implement a programming language to do bigger things. So, for example, I just asked one of my students to write the following program, which should be about 5 lines. There is a site which keeps track of, which keeps copies of out of copyright books. So you can get Mark Twain's books at that site. I've forgotten the name of the site. It's somewhere. Anyone know? Yeah, Gutenberg. Gutenberg has lots of good books, excellent books. And it keeps them in compressed form. So I would like to write a program that will go there and pick up the titles of 5 of the books they have and prompt a user to choose one of them. The user chooses one of them. And then it goes and gets that file and gives that file to some other service that will uncompress the file. So we get the uncompressed file. Then take that uncompressed file, give it to another service that will pick out the first 1,000 words from that file and create a new file. Okay, we get a smaller file. Take that file, pick up the first word from it, and send it to a Google spell checker. Such a service is available. It's called Google Spell Checker. And Google will spell check that. Huckleberry. Well, no, I don't find any Huckleberry here. Huckleberry Finn, if you're thinking of it. So it will suggest something. And then my program will take the second word and ask the Google spell checker to check it. So check out the first 1,000 words. Okay, this is not a very interesting application. We haven't done much, but this will give you the idea of the kinds of things we are capable of doing today. And I would like to write programs to be able to do this. Further, I want these programs to be very, very short and simple because I can explain them to you. It's short and simple. You take it there, you get some data from there, you move it there. And the whole point of being able to write this, or the whole idea behind writing these programs in a short fashion is that we don't do any work, we cheat. We take it from here and move it there, and take it from there and move it there. We don't interpret anything that's happening in the middle. We don't look at the data and do some work ourselves. In fact, if we want to add two numbers, we would call a service that adds two numbers. How can we do anything with this? What's the model? What's the advantage? Why not write Java programs? So let's go on with my main talk, and I'll come back to some demos in a second. So here is a simple problem that I would challenge you to solve today. Contact two airlines simultaneously for price quotes. Let's say I'm coming from Austin to Raleigh, and I would like to contact, let's say, American and Delta. Buy a ticket from either if the quote is at most $300. Buy the cheapest if both quotes are above $300. Buy any ticket if other line doesn't provide a timed quote, like I'll wait for 5 minutes. And if one airline doesn't come through, I'll just buy this other one. And notify me if neither airline provides the timely quote. Okay, we can write the specification reasonably clear in that much space. Why can't we write a program which is about that long to do this job? Because after all, airlines are already providing that service. They will give you a quote of some kind. And the only logic involved is something about time and just $300 and getting something first and looking at it. And it turns out that we don't, in current languages, have these facilities. It's too involved. If you think of, say, expanding Java, adding more features to it, you don't do it very well. And this will be one of the problems that I would like to solve. So when I started looking at this area, I saw that the main problem is this. You want to get data from some remote services. You want to do some computation with this data, and you want to call yet other services with the results. Of course, I'm not going to do any calculations. I'm going to call other services to calculate with the data also. So all the time, I'm calling services to get data, and again calling services to do something with the data. But additionally, we want to do things like this. We want to call a bunch of services at the same time, perhaps, because they can be done in parallel, or we may be expecting one of those services to fail, and we want to sort of have something else come through. Or we might want to repeatedly poll a service or ask the service to notify me when it acquires the appropriate data, or download an application and invoke it locally, or have a service call another service. And once you start writing down the kinds of capabilities you need, it becomes something like 57 things that you should have. And then I wondered, how do people actually solve it? When you go to practical commercial systems and you see all 57 features are there. No, they're all written down here. This, you want to do this. So if you want to do anything novel, it's impossible. How do I put this together? I can't keep all this in my head. So the research challenge is there something fundamental with which we can build all of these things? How small should it be? And this is a challenge I put to myself. And I think I have somewhat succeeded, because we have been working on this for 2 years now and we haven't been able to break it. And the answer, can anyone guess how many features you need in a language to do this? Anyone read my abstract? 3. Okay, so let's see how far we can go with 3. So here are the 3, well, this 3 is different from that 3 that I just told you. These are the major components of a distributed application, that you should have some method of managing persistent data. So airlines have to have their databases. And if you call them, they should be able to look up their database and quote you a price or something. That's not the problem that I'm going to solve. It's an important problem. It has a new meaning in the world of the internet. There are all kinds of new data that they have to keep. A very interesting research area. I'm not working in that research area right now. Then there is the question of sequential computational logic. Does the ticket price exceed $300? Suppose I come here and I run my expense account through this program. It has to add up the cost of the hotel and the rental car and the airfare and other such things. So somebody has to do the addition. That's sequential computation. Again, I'm not solving that problem. Somebody else will have to do it. What I'm interested in is orchestrating the computations. What does that mean? It means that you have to do a step before you do another step. You have to get a file from somewhere before you start uncompressing it, and before you start doing spell check on it. So there is a sequentiality. You may have to do certain things in parallel, so you can do them simultaneously. You may wish to start several things simultaneously, but once you get a result, you may want to kill off other computations that are going on. So I am more interested in setting up the computations and saying that this computation consists of calling the services and name the services, but I'm not going to do the real work. So in other words, cheat as much as possible. So we're going to cheat. What does that mean? I devised a language called ORC. ORC stands for orchestration. I also understand it stands for horrible animal in some movie. Yeah, I saw the movie twice. I couldn't understand it. Oh, I see. You understood it? I couldn't. But a 6-year-old explained to me that it is true. There is such a thing. I trust it. So let's go on with it. It's not really a language. I mean, languages have to have many things. So when I say it's a language, it's not a language. It really is a set of constructs, concepts, features. You can overlay them on a real language like Java, which will provide you with data structures and other such things. And you can do a lot of things with it. So right now, the programs that I showed, they're all in ORC. But then to do anything useful like services may have to be written in Java. How do you uncompress a file? It may have to be written in Java. And here is the first page of the manual, and that's almost complete. No, there is a second page. So an ORC program is based on expressions. You write an expression. It's called a goal expression, and you would like to evaluate it. But just writing a long expression will not do the job if the program is sort of 30,000 pages long or something. So you want to modularize it by putting some definitions in it. And the goal expression will refer to some of these definitions. So that's what an OR program. That's what a program is. So a goal expression and a bunch of definitions. And the program execution just evaluates this goal expression. And in order to evaluate this goal expression, it calls certain entities that are just services. They will provide services. And give it a neutral name called a site. So there are a bunch of sites that I expect are available, like uncompressing a file, or checking spelling, or adding 2 numbers. And the expression evaluation will call these services to get some results, and eventually it will publish some values. By publish, I mean, as in a functional program, there is one answer that comes out at the end. There will be many answers coming out of a goal expression, and those are the publications. So what happens to a publication? Just think of it like it's going into the ether. You evaluate this, the value is such and such. For the moment, that's what we'll do. I wish I had not written this word simple. That's all in the eyes of the beholder. So never write such words. Dijkstra once told me that I often see people here say things are very natural. Natural is a word like Christian. It roughly means nothing. So simple means nothing. The only thing I can say is that language has only 3 combinators to form expressions. And the other things are somewhat theoretical. I won't talk about this, but I'm very happy with this. If it were not true, I would be unhappy. So this is the manual structure of an ORC expression. The ORC expression comes in two forms. Either it's simple or it is compound expression. A simple expression looks like that. You call a service, let's say there is a service called CNN, and you give it a parameter D, it might be today's date or something, and that thing is an ORC expression. The effect of this ORC expression is to call the site CNN with this parameter, wait for its response, and when it gets the response, publish that value. So it looks like any other thing that you know, nothing big has happened. It's just an ordinary expression. But then, once you have expressions, you can build longer expressions by combining them. You can combine two ORC expressions in three different ways. So there are three combinators, and each of these combinators does something different. So do two expressions f and g in parallel is written in this style. You put a bar between them and f and g. I will go over this in detail because that's all there is to it actually. And then we have two other ways of combining them. This says that for all x from f, do g, and this is called sequential composition. And the next one is for some x from g, do f. This is written in the opposite way, and that's asymmetric composition. So what I'm going to do is to go quickly over the semantics of these in an informal fashion, and I'll show you a number of things that you can do with this. So my hope is, in this 1 hour lecture, to be able to convince you that there is something here that we can use to build large programs. But of course, in 1 hour lecture, I can't really convince you, so I can give you some plausible arguments. So let's start with symmetric composition. As I said, you expect to do f and g, or you evaluate f and g in parallel. And the idea is you do them independently. And so f will run independently. It will call some services. G will call some services. And they will publish some values. So whatever values they publish all the values from both as soon as they occur. And the important thing is there is no direct communication between f and g. Some of you who may know other process algebras like CCS and CSP and pi calculus, they have communications, they have synchronizations. There is none here. It's pure independent computation. So for instance, if we wrote this, CNND bar BBCD, its effect would be to call both CNN and BBC simultaneously. And as soon as it receives a value from either of them, it will publish it. So it may publish any number of values from 0 to 2. Because CNN may not respond, BBC may not respond. If both respond, we get both values. By the way, I teach a class, an undergraduate class, at 3:30 in the afternoon. So most of them are asleep, about 20 minutes. And once I tell them, I give them a rousing story, idealism and everything. How about making an effort today, just once, that no one will sleep? I have really prepared this lecture in great fashion. And within 10 minutes, about 20% were asleep. The point is that one way I have found to keep people from sleeping is to ask them questions. The other is that I encourage you to ask me questions. That keep your neighborhood at least in a non-sleepy mode. So please feel free to ask questions. So is this clear that you can publish something between 0 and 2 values? So my expectations for services or sites are quite low. I don't expect that they will return a value, or I don't write my program assuming such a guarantee. They may or may not. One thing though is that each service will respond at most once. So if I call, I expect at most one response. I don't expect a stream of responses. That's one thing. That's one property I expect of a service. If you want a stream, you can program it, but you'll do some extra work. Now, here is sequential composition. And the idea here, as I said, for all values from f, do G. What that means is, if I wrote, no, let me not do this. Start evaluating f, and whenever it publishes a value, bind that to x, and start a new instance of G executing with that value. That's the idea. So actually, this is a much better thing to show. Here is on the red line is an execution of f. And these are the points where f is publishing a value. And each time it publishes a value, we bind that to x and start a new copy of G. So G0, G1, G2. So at this moment, we have 3 copies of G running concurrently along with f. So this is a generalization of what you see in, because I use a primitive drawing system, and I could, as in Xfig. Xfig was done by a colleague of mine. I learned it. I'm too old, busy, etc. to change. Also has that novelty of what could he have possibly meant here. Yeah. So that's what FXG is. So what does that mean? When I take this expression, this is a very simple one. It calls CNN, and when it receives a response from that, it binds that value to X, and it calls this service. This is email service. Let's assume that email sends a mail to this particular address, which is available elsewhere, and with that argument. So these are the steps that will happen. Call CNN, bind result, call email. And the value published by this expression is the value published by the last part. Any value published by CNN is consumed internally with this X. So this is pretty similar to what you would do in a normal Java program. You will put a semicolon to say this is the first part, that's the second part. But what's different is when you go to this example. Here we have, this is the first part and this is the second part. Here we'll call CNN and BBC simultaneously. And we may possibly receive 2 responses, one from CNN, one from BBC. And with each response, we'll call email. So we may call email twice, up to twice, and it will publish up to 2 values from email, whatever email does. And that's interesting because it will start up a tree of computations. And we can do it. If I get a chance, I think I have that example. I'll show you a very nice example of a problem that has been solved by many people, and I'll do it slightly different.
I have a question which I'm sure others are also thinking of. So with the sequential composition, you only produce one answer, but with the others, you're assuming it's a stream of answers. You know,
With sequential computation,
you have
which one?
the previous page, you would only, I'm sorry, symmetric composition.
Yeah.
You would only produce one answer out of F.
No, you publish all values from both. So this one publishes.
Okay, that's just that particular example. Okay, I'm sorry, I misread it.
Yeah, this can publish up to 2 values. And in fact, that's the reason we're seeing this problem here.
Yeah.
Okay, so yes. The site call ends when the site responds. The call, of course, ends as soon as you call it, and you don't know if the site is ever going to respond. But once it responds and you receive the response, you know that it's finished. If the site has not responded, you have to keep on waiting because it may respond sometime in the future. Yeah, in the example, we never know when f is finished. We keep on waiting for it. If we know the structure of f, like it's CNN bar BBC, we'll know that after 2 answers we're finished. But in general, if we don't know the structure of F, well, a program always knows the structure of F. But if there is recursion or some such things involved, you do not know if you're ever finished. I'm going to use a bit of notation, but I hope this notation is so simple and small that you won't bother with it too much. I'm going to take out this x if it has no relevance. If, for instance, I never use this x in G, then I'll just write it like this. And also, I'm going to have the sequential composition have precedence over bar. So I will write it this way to denote this particular expression, which is parenthesized. And further, this is going to be associative, so I will write it without parenthesis to mean just this. Asymmetric composition seems to be a fairly new idea. I haven't seen this anywhere. In fact, I had a long talk with Robin Milner 2 weeks ago, and he was quite intrigued by this. I don't think he has got it, but I believe this is an important idea. This is what I've shown you so far. If you think in terms of threads of computation, I've shown you how to create more and more threads. Okay, I put bar and I created 2 threads. Then I put a fxg, and every time you start something, you create a new thread. So this is the way of creating new threads. More and more are being created. So there has to be some way of killing threads. And this shows how to kill it. The idea here is it's almost like the other case. You, for some value published by this side G, you push that value into F. And you want to do it for some value, just one value, not all values. And we're going to take the first value. The first value that G produces, we want to do F with that. But there are some subtle differences than from what I just told you. I would like you to start with this example. Here is G. I don't know what it is, but here is the F side, the left side. And what I can do is start executing F even though I don't have the value of X. How can I do that? Well, here I can call M. I don't need the value of X for that. But then I would like to do this too. I can't because I need the value of X. So it is suspended. We're waiting. At the same time, we'll start running G also. As soon as G publishes a value, if G never publishes a value, we will just wait on that left side, N of X, because we don't have the value of X. G will keep on running. But suppose G publishes a value, we'll bind that value to X, and now we can use this, N of X. We can call N. Additionally, once we have a value from G, we don't need G anymore. We need just one value. We'll kill G. And what does kill mean? We will do nothing that happens within G. We will not call services from G. We'll not look at any values. What about some computation that I may have started, which is halfway? Suppose G called 2 different services. It received a value from one service and it's waiting for the other. And it published that value. We are happy with that value and we want to terminate G. So what happened to all the requests that I had sent to the other service? Well, we can't unrequest that. When the answer comes to that request, we'll ignore it, throw it away. So, as before, this is what we do, evaluate F and G in parallel. When G returns a value, assign it to X, terminate G, and resume suspended calls. And the values of this expression are the values published by F. The value published by G is consumed internally. So this is the manual. This is a manual. We're finished. And, well, we're almost finished. There is just one more concept. But, okay, what happens here? As I said, we would evaluate this right side and this left side simultaneously. We'll start them out. Yes? Microphone?
I'm not sure if I'm actually asking you the question well in advance, but what kind of assumption do you make about the structure of solution returned by one of your function calls? Like when you say CNN of t, so what is the assumption you make about the
Type of value?
the format of the output?
Good question. I make no assumption. As I told you, the easiest thing is not to make any assumptions if you don't process the data. Right? If all you do is send the data to some other service, then you don't have to process the data. I will, in my examples, I will show you some structure that I'm expecting to get a list or I'm expecting to get a tuple. But beyond that, I make no assumption. And I will tell you why, because it cuts down on the amount of implementation work you have to do. If you are expecting to receive an integer and it doesn't send you an integer, you have no control. You don't know. You send it to some other service which will not like it and give you an error message. But in the practical implementation of the language, the students have actually put in some types because they need it to do some trivial things, otherwise which will become very long. But in the pure Ort language, there is no assumption about the type of value.
Because when you show this example where you pass the value to say email, so which means your the output could be possibly relational or something, from which you pick up X and give it to email?
No, it's not relational. Okay. But what you're asking is whether it could be a tuple, and I take one component of the tuple. Yes. So there is some structure that I will assume here, like tuples and lists that are available, which is implemented. But no, in general, I will not make any assumptions about whether I'm receiving. For instance, we wrote a large system in which the data was XML. And Alt didn't do any work with that. All we did, whenever we want to parse it, to send it to another service and say, give me that part of the XML query. So if you start doing data, it becomes it's a huge language with types. So let's look at this example. The left side and the right side are evaluated right away. To do the left side, we get stuck right away because we don't have the value of X. So it's suspended. We're waiting. But we can do something with the right side. We evaluate the right side means we start this and this, CNN and BBC simultaneously. We call them. Let's say that CNN responds first. As soon as it responds, we bind that value to X, and we can now resume this particular expression evaluation. So we call email with that value of X. At the same time, we terminate this side, which means we are going to ignore any response that we receive from BBC. So this program will send at most one email, unlike the previous one, which might send up to 2 emails. So whichever happens first will do it. So all I require from the rest of the world is that you provide me with 2 or 3 services. One is this service, if, and the input to that is a Boolean, B, and it returns something called a signal if B is true, and it remains silent if B is false. What it means, a signal is a unitary piece of data. It has no value in it. It just comes. Silent means it never responds. So if you call the if site and give it true, then you will immediately get a signal. If you call it with false, you will never receive a value. So if is encoded as site. Stop is a site which never responds, which is same as if false. Very useful, by the way. Do you know that? I intended to put that in because it sort of worked like the zero of an algebra. But it's used practically all the time in writing large programs. You want to cut out threads, just put a stop. Signal just returns a signal. It's same as if true. And the last one is quite important. I call it R timer. R stands for relative, which takes an integer as input, a positive integer, non-negative integer as input, and it returns a signal exactly t time units later. So right now our time units in our implementation are milliseconds. So if I wrote R timer 20, then exactly 20 milliseconds later, I'll receive a signal. There is no notion of time built into ORC except through this, and that is it. And we'll be able to do a few things with this. So imagine that an expression is evaluated on a single machine that I'll call client. That client communicates with the sites by sending messages to them. And all fundamental sites are local to the client. All except our timers respond immediately. And I won't explain the last part. This is the model the programmer should keep in mind. It's not the true model, because if you write a large program, you can't have a centralized execution. It will be distributed, but the programmer shouldn't worry about it. We will take care of distribution. We'll make sure that when we distribute, we support the same semantics as a centralized model. So that's a trick. We don't ask people to say this is a process and that's a process and that can go on this computer. I think in reality, it's very difficult to manage that. So we'll keep a simple model and manage to do everything automatically. The last part of the language is definition facility. So here is a little program which you have seen before. It sends to an address A at most one email. So I'm giving it a name. I'll call this mail once, and that's this expression. It takes as input A. M is a bound variable in this expression. That's the expression. As soon as you have this facility, you can see that you can put the left side name on the right side, and you can get recursion. And that's the only way you can get unbounded computations. What I've shown you so far will not give you unbounded computations. It is bounded. And the unbounded computation here, mail loop AD, just imagine D is an interval, like a day. And here I start out by calling mail once A, which will send at most one email to A. And then it waits for D units of time, maybe a day. And then it goes back and redoes this program. So effectively, every morning, it calls the two news sites, gets one response from them, and emails that. And it keeps on doing it forever. So that is the conclusion of the model. It's taking me a little longer than I had expected, but it's more important that you understand it. Are there any questions before I show you some examples? Yes?
I'm just curious how you decided that the three particular combinatorial facilities you have were the right three or the only three you needed.
Yes, that's a very important question in doing any research. The short answer, I don't know if these are the correct ones. Just like in any process algebra, you can come up with a number of combinators. And the only way you can sort of justify them is by empirical investigations. You try a number of benchmark examples, you see how you're doing. You have some theoretical ideas like, yes, these combinators have nice properties, like they're monotonic and continuous. Those are nice properties. You try what other people have done and show that you can simulate their combinators. That shows that, well, maybe it's as powerful as pi-calculus or CCS or something. That's one thing. But what I can't prove to you, that I have got it in exactly the right form. Maybe these two combinators overlap somewhat, and I could have created something better. I don't know that. I suspect they don't overlap too much if they do. But no, I don't have a theoretical answer to your question. Would you like to?
What about the error handling mechanisms? For example, if I can't constrain, if there is more than 10 gigabyte data, just ignore it. Or
Yeah, that's the really important problem. That unless you can handle error, what are you doing? Internet is a computer. If everything worked perfectly, we won't need any of these problems. We can write in Java. Just tell this data is available there and that piece of data. And some of the examples I will show next will probably answer some of your questions. Here is a little example. I'm defining something called metronome. Metronome publishes a signal every time unit. How does it do that? Well, it starts by publishing a signal. It waits for 1 unit, and then it calls metronome. So how do I say this? How do I say this? On the one side, I have this, which will publish a signal immediately. On the right side, I have an expression that waits for 1 unit and then behaves like metronome. And if you want to look at it a little more carefully, we are starting 2 threads. S stands for signal and R for this right side expression. So we do these 2 things independently, and this will publish a signal. And then the right side is R and this entire tree, the same tree. So this does the signal and it waits for 1 unit. So this goes on forever, publishing a signal. Why is that interesting? Let me take up a little problem. Suppose I have an expression. I'll call this gen I. It publishes these values starting from I plus 1, etc. at unit intervals. Suppose I can write such an expression. It will be like metronome. So gen 3 will publish first 3 right away, then 4 1 unit later, 5 2 units later, etc. Go on forever. Suppose I have a site prime n, which returns n if n is prime, and it doesn't do anything. It doesn't respond at all if n is not prime. Write a program to publish all prime numbers. And here's the program. What I would like you to note is that there is no explicit loop here. There is no explicit recursion here either. I'm not showing it to you. There is no recursion. It's straightforward. It goes from left to right. What's happening is the structure of sequential composition. Every time it publishes a value, it will start up a new execution of this. So the recursion is hidden inside this gen 2. It's producing a stream, and for each value of the stream, we're taking up and doing something. And this is a paradigm which we found to be quite useful. It simplifies programming. You don't have to explicitly show a loop or a recursion or something anytime you want to do something unbounded. Timeout. Here is one answer to your question. That I would like to call a site M and publish its response if it arrives before time t. Otherwise, I want to publish 0. Well, what I would do is take this expression on the right side. What does it do? It calls M. At the same time, it calls R timer t. Suppose I get a value from M before t time units. That value will be published. That will be the first value. It will be bound to z. And I will publish z. But suppose I wait for t time units, M doesn't respond, then this is going to publish as 0. That will be the first value published, that will be bound to z, and that's what I'll publish. In the meantime, if any value is published here, the rest of the expression, execution, is terminated. Okay, we can leverage this. We can use this to get all kinds of different timeouts. Let me go on. Maybe some of the other examples will show how we can do this. This is a paradigm that's much loved by people in concurrent programming, fork join parallelism. You want to call the 2 services in parallel and proceed only after both of them respond. We don't have that. There is no such combinator. But this is what we can do. We can output a tuple u and v, where u is from m and v is from n. Remember that this thing in black is one expression, and this expression has v followed by n. How do you evaluate this expression? You start evaluating the left side, and you call n. As soon as n is bound, as soon as n produces a value, that will be bound to v. Well, good. How do you evaluate this expression, the internal expression? Well, you start evaluating this and also call m at the same time. You can't do anything with this because they're all unbound. So effectively, you have called m and n at the same time, waiting to receive their responses, and only when you get both of them, because otherwise this can't be evaluated, only when you get both of them, you output them. So this structure occurs so often that I'm going to just write it this way without any parentheses. It's left associative. Or quite often I write it this way because it's easier to read. And we get fork join. You can do barrier synchronization the same way. But let me show you a harder problem. It's a practical problem. I have a list of students that I teach, and if they've done very well, I invite the top 3 or 4 students to join my research group. At one time they would jump up. Nowadays you don't hear from them. So this program will send a email, call some sites, a number of sites, and it counts how many responses you receive within a certain time period. Just a count. I'll call that count tally, and the input to this program is a list of sites. So call all the sites in that list simultaneously. Wait for 10 time units, and then publish an answer. How many responded in 10 time units? Now, we write it in this way. The style is very similar to functional programming. If your list is empty, your answer is going to be 0 because you aren't going to call anyone, no responses received. If your input is of this form, the first entry is M and the rest of the list is MS, what I would like to do is store in U this quantity. This quantity is going to be 1, the result, the integer 1, if M responds within 10 time units. It will be 0 if M does not respond within 10 time units. And you can see the structure that we run these 2 computations simultaneously. Whichever publishes first goes into U. At the same time, run tally on the rest of the list in parallel and store the result in V. And the answer you want is U plus V. The point I want to make here is some of you might be familiar with functional programming, and you see a great deal of similarity here with functional programming. Realize that this is not functional at all. There is a great deal of non-determinism here. Which one? There is a timer involved here. There is a abortion of computation at some point. Halfway through, some computation is terminated. In fact, a whole bunch of these computations are terminated recursively. And yet, we can reason about it in a fairly functional style way. And that I felt was sort of important when I wrote this, that maybe we have something going here. Let me skip this. Barrier synchronization, that's quite easy. Priority. Let's just do this. I want to call a site N, and I would like to receive its response, but I don't want to receive it quickly. Strange thing. Why wouldn't you want to receive it quickly? No, I don't want to receive it quickly. Just hold off. So I want to call an airline, and now I'm going to go get a cup of coffee, and I'll be back in 10 minutes, and I don't want to receive that response for 10 minutes. So these are the new paradigms for internet kind of computing. You don't see them in operating systems or anything. So how do you go about this? It's strange, but let me suggest that one way to think of it is that you are running 2 threads of computation. You are calling the airline, that's 1 thread of computation, and you are calling a timer with 10 minutes, that's another thread of computation. And you want to do a fork join on them. And that's what I'm doing here. So I will run this on 1 thread. I will have R timer 1 followed by output U, and the U is going to come from N. We understand this by first evaluating this expression and this simultaneously. So we're going to call N right away, and we're going to call R timer 1 right away. Now, suppose this responds first. N has been tardy. Then we'll come here, but we can't output this U. We'll be waiting. And when N responds, that's fine. So we waited at least 1 unit. But suppose N responds right away. We're still waiting for this one to finish. And only then we'll output U. So this delays artificially by some amount a response that we could receive. What is its effect? Well, I want to solve this problem where I call M and N together. If M is my favorite site, let's say M and N are airlines, American and Delta. Let's say I like American, which is not true, but let's assume that for the moment. And I want to give a little extra to American. So I'm going to wait for 10 minutes. Within 10 minutes, if American responds, I'll take its response, irrespective of when Delta responded, before or after. But I have a limited patience. After 10 minutes, if American has not responded, then whoever responds first, I'll take it. And as you can see, that's very easily done. Just run M and run delay simultaneously, just delay. And publish whichever comes first. How much time do I have? Here's the clock. 3 minutes? 3 minutes, good. Okay, interrupt can be done. Parallel OR, this is an important one. This was actually a very important one. I mean, in my own research, I wrote down several semantics of that asynchronous composition, and I had to use a particular semantics to get this right, and I think it's the right one. Parallel OR comes up in a number of contexts. You may have heard of it before. The problem is this. Suppose you have two sites which respond with booleans when you call them. They may or may not respond, but when they do, they respond with true or false. If you get, and you are supposed to take the logical OR of the two values that you get. But if you see a true from one of the sites, you can publish that right away without seeing the other one. And that's quite difficult. You can't do it in functional programming because you have to choose one or the other. We can do it here because it's all symmetric. This is the way we'll do it. We'll call M and N, the sites that are supposed to return Boolean, and this is the main expression that's running. If X is true, then publish a true. If Y is true, then publish a true. Otherwise, take their logical OR. OR is a site, just logical OR, and publish that. You see that if suppose M responds with a true, then immediately this branch will publish a true. Suppose M responds with a false, then this is silent, it won't publish anything. But maybe Y will come through and it's true, and then this is going to publish. But then this is also going to publish, because OR of XY is now can be computed, so it will publish. So do you all see that we'll publish the first true as soon as it comes? You also see that you also might publish a whole bunch of other things. Like if they're both true, what will happen? We'll publish three things, right? The first branch will publish, the second. We don't want that. We want just one value. How do we get one value? Yeah, we know how to cut out everything else by doing this, right? Call that Z and publish Z. That publishes one value. So that's it. So there are a lot more I could show you, but I don't have time. So let me finish with where I started. The airlines example, where I said, as soon as I find a value below $300, buy the ticket. That is parallel OR. It says that as soon as you see something that meets the criterion, act upon it. And unless you have the solution, you can't solve that problem. So with this, it works, of course, trivially. I will not be here tomorrow, but I'll be at Duke and UNC. So you're welcome to come there and talk to me, or you're welcome to send me email. There is a website which is quite nice. I may have shown it to you. So I encourage you to go here, and this is mostly done by my students, and they promise to teach ORC in 15 minutes, so you don't need a whole hour. Thank you so much.
I think since we have sites, other sites connecting and they may be disconnecting, we'll give them the first priority in asking any questions. Are there questions from remote sites?
This is exactly what happens in Orc. You send out a request and you're just waiting. All right.
Maybe they can hear you better. You can ask them for questions if.
Would the remote site like to ask any questions?
Yeah, I have one question. My name is Lakshmi Narasimhan. I'm talking from East Carolina University at Greenville. How does these semantics, go with, say, for example, WS eventing, web services eventing?
Yes. Let me repeat the question. So how can I exploit service? I don't want to use the word service. How can I exploit constructs like WSDL, SOAP? Is that the kind of question you wanted to ask?
Yeah, somewhat similar to that. Now, there's a specific
Roughly speaking, I don't know the answer,
WS
but I know it's
eventing.
very painful. Let me tell you what the problem is.
Okay.
I expected that the rest of the world will develop some standards by which services can talk to each other. That's the next logical thing to do, I felt 5 years ago. And there was some standard called WSDL, WSDL, and SOAP, and they were unusable, but then I felt that some new standards will emerge. And this is one area in which I have been hugely disappointed. It is wasting a lot of time because every web service provides a different interface. It doesn't work very well. WSDL is extremely hard. It wastes a lot of time. Recently, they have come up with a standard called REST, R-E-S-T, which seems to be slightly better. That's what my students tell me. But it's really impeded our research. By now, we expected to have hundreds of sites that we can talk to. The only set of sites with which we are reasonably happy are the Google sites. They seem to be reasonable in publishing their APIs so that you can talk to them. Google Spell Checker we use, Google Search we use, Google Calendar we use. In fact, one of the demos that I couldn't show was to go look for all kinds of bands that are playing in Austin over the weekend and put their names into your Google Calendar and send emails to your friends when a particular band is playing, asking them, do you want me to buy a ticket for that band? Respond in 30 minutes. It was a very short program, about 5 or 6 lines. But this is the kind of thing we would like to do with many other sites, and we have not been able to do it because the standards aren't there. And we are not in the standards business. We wanted to use standard protocols to talk to services. It's not there. Well, I probably answered a tangential question, but something has been answered. Okay. All right. Okay, local sites. Any questions?
Thank you.
Must have answered all the questions during my talk. Thank you. Oh, there is a question here.
Yeah, so I was wondering, so you're depending on a fairly strong standardization in terms of what a site will return and what a site will accept at some point, right? So because as of now,
not what it will return, but its signature. It needs 3 parameters. One of the parameters has to be integer, one has to be a date, one has to be a string, and it will return something. I don't care much about that something, but I want to know how to call that site and how many parameters it takes and what they should be like.
But logically, or even if the parameters remain the same logically, so at this time we find, for example, a site which used to return, I'm just talking about websites and human operation, it used to return plain text. It returns the same information now, but embedded in a huge XML document with nice flowery borders and so on. So so until there is a very strong standardization there, doesn't this sort of move the burden from the programmer to the programmer of the compiler, if you will, whoever has to, your students that have to maintain ARC, as it were?
Yeah, this is a real problem. True. So roughly speaking, you're asking, suppose yesterday the arithmetic unit, addition unit was adding, but now today it's multiplying. So how do you maintain your program? Yeah, that's the real problem. And you do get all kinds of errors. Actually, they don't send HTML documents that much. XML is the standard now, and we're a little more hopeful because XML is at least, in some sense, have some kind of a grammar somewhere at some website. So you can do slightly better. But no, I agree with you. It's a true, very hard problem. So if you want to build an internet computer, there should be some places where services are going to be standardized. Maybe the location is not standardized. I call that location, it might redirect me to another location where that service is available. That's fine. I don't see that. That becomes transparent. It just wastes a lot of time. But that's fine. But if it changes its interface, it's very difficult to manage. Right?
Ooh, it's loud. I was going to ask, what do you think are the network traffic implications of this? I mean, we've already seen that things like peer-to-peer traffic are consuming, or at least people, certain people are afraid that they're taking over the internet. I mean, I don't think that's true, but that's a problem. If you're having to do well, not every, but a large percentage of your calculations using machines which are somewhere else, puts a lot of burden on the internet, wouldn't you say?
Yeah, true. And the way to treat it is to assume that that's an infinite resource which is provided by someone else. The practical answer is that, and this is not something we have done, the practical answer is when you see that you are using a service over and over, to automatically migrate that service to your local computer without the user knowing it. These are optimizations, and they're important optimizations. I was talking to some people in your department who are doing some very interesting work on orchestrating grid computations, and they're moving huge amounts of data from one place to another. So today, terabyte does take a lot of time, and petabytes just can't be done. It's just too much. And I don't know how to solve those problems. But I suspect that we'll have migrations happening automatically, depending on traffic pattern and other things. But I won't worry too much about whether the network is getting saturated. Yeah, somebody can't watch NFL, it's their problem.
Can you say a little bit about how you would maybe distribute this across multiple systems? I mean, we've talked about a central computer here, and you made a few remarks.
Yeah. Would you like to invite me back as distinguished lecturer again? Because that's a talk. That's a full hour talk. But let me give you a 15-second answer. I would like to take an expression and analyze it and figure out that certain parts of it can be independently evaluated. For instance, if I take f bar g, almost always I can have f running on one computer, g on another computer, and the effect is the same. The one exception to that is f and g are both referring to the same clock. They're referring to our timer. And we can't distribute the same clock perfectly across both machines. But then it's not as bad. It sort of goes, sometimes they are both referring to the same clock, but their effect can be masked. You can figure out. So there is a theory that I have developed, which is not complete, but it's almost there on how we can distribute it. There is a distributed implementation which works on a conservative aspect of this theory, and now we are sort of aggressively making it distributed. So instead of actually the user specifying that distribute this, we figure out what can be distributed over the given machines. In fact, we are running multiple servers just for that. I don't think this will work if you have to do everything on one machine. The whole purpose is lost. You want to build process networks, so you must actually distribute them. So if no timer is used, as you well know, if there is complete asynchrony, you can distribute. F and G goes into two things, F, X, G, F on one machine, G on another machine. Similarly for the other ones. So it's completely...
Is there a distinction between local sites such as if versus remote sites? I guess email, CNN, they're remote sites. You said some slides said something
I'm embarrassed to admit there is a distinction. I don't quite understand it. We use it all the time. Roughly speaking, local sites are supposed to respond immediately. They never fail, and they're supposed to respond immediately when they should respond. So if false, will not respond. If true, should respond immediately. There is a notion of time. There is an R timer. And we do exploit this fact. But the semantics of this, well, no, actually we have the semantics, but it's not something very easy to explain right away. I wish I could, but I don't have that explanation. That's a lot of questions, so I think I've kept you all awake. Thank you again.